In this lesson, we're going to learn how to separate metal ions from aqueous solution by selective precipitation. In a selective precipitation, the identities of the metal cations that may be in solution are known, and we would like to separate and remove them. The solubility rules and differences in Ksp or Kspa values are used to find unique ways to precipitate one metal ion at a time while leaving the others in solution. We'll begin by selectively precipitating ions whose precipitation involves a metathesis reaction that's independent of pH. The exceptions to the solubility rules for ionic compounds can be used to selectively precipitate ions that are exceptions and leave in solution those that aren't. Another selective precipitation method involves increasing the pH to precipitate metal ions as hydroxides one at a time. When the pH of the solution is adjusted upward by adding a base like sodium hydroxide, most metal cations will precipitate as hydroxides. As the pH is adjusted to make a solution more basic, metal hydroxides with the same metal valency will precipitate in order of increasing hydroxide Ksp. Another method of selective precipitation that we'll discuss tends to be messy and creates an unpleasant odor, but it's the most effective method to separate some ions. Adding sulfide to solution causes metals to precipitate as metal sulfides. Different metal sulfides precipitate at different pH values, because dissolving or precipitating a metal sulfide is just one part of an equilibrium that includes a reaction with water to form a diprotic acid. As the pH is adjusted to make the solution more basic, sulfides with the same metal valency will precipitate in order of increasing Kspa, which is a type of solubility equilibrium constant that's unique to sulfides in aqueous solution because it takes into account the reaction of sulfide with water. Let's begin with a simple selective precipitation that's based on a metathesis reaction that's independent of pH as long as all of the metal ions are initially dissolved. Most metal halides are considered to be soluble in water. Lead 2 and silver cations are among the exceptions that'll form sparingly soluble chlorides. If we add chloride to the solution, usually as hydrochloric acid or sodium chloride, we can precipitate most of the lead and silver as chlorides. Let's selectively precipitate 0.05 molar silver ion from 0.05 molar nickel 2 by adding sodium chloride until its concentration is 0.1 molar. That's 0.584 grams solid sodium chloride per 100 milliliter solution. We know that silver ion will precipitate as silver chloride, but nickel will not precipitate as a chloride because silver is an exception to the rule that metal chlorides are soluble. Let's look up the Ksp of silver chloride to find how much will remain in solution when we add the sodium chloride. That will help us to see how effective the precipitation will be. Substitute the concentration of added chloride into the Ksp expression, treat it as a common ion, and solve for the concentration of silver that will remain in solution. Only 1.87 times 10 to the negative third molar silver ion will remain in solution. This is only about 4% of the initial concentration of silver ion, so about 96% of the silver will precipitate, leaving the nickel. We would expect the separation to be even more efficient if we added more chloride to the solution, because chloride decreases the solubility of silver chloride due to the common ion effect. Next, we'll separate metals from solution by adjusting the pH until they precipitate as hydroxides. The different Ksp values of metal hydroxides dictate at what pH they'll precipitate. Let's separate metal ions from a solution that contains a 0.1 molar concentration of two alkaline earth metal ions, calcium and magnesium. First, we'll determine at what pH each metal will precipitate as a hydroxide, so we know below what pH we'll need to start and at what higher pH to stop for the best separation. Look up the Ksp value for each metal hydroxide and set up a Ksp expression. Remember that when the concentrations of ions satisfy the Ksp condition, the solution is saturated. The concentrations of the metal cations are known, so they can be substituted into the expression to solve for the concentration of hydroxide needed to saturate the solution. Next, calculate the pH. Magnesium hydroxide will begin to precipitate at a pH of 8.874, and calcium hydroxide will begin to precipitate at a pH of 11.851. That means the best separation will happen if we raise the pH all the way to 11.851, where calcium hydroxide is saturated but won't precipitate with the magnesium hydroxide yet. Let's find how good the separation is by substituting the concentration of hydroxide at a pH of 11.851 into the Ksp expression for magnesium hydroxide to find how much of the magnesium will still be in solution at a pH of 11.851. It turns out that only a small fraction of 1% of the magnesium is still in solution. Selective precipitation of hydroxides is often a very efficient way to separate metal ions from solution, especially when the Ksp values of their hydroxides are very different. Next, we'll selectively precipitate metals as sulfides. Precipitating metal sulfides is a strongly pH-dependent process because sulfide also reacts with water to form an acid. Sulfide is usually put in aqueous solution as an alkali metal sulfide. It accepts protons from water or acid to form hydrogen sulfide, which is also known as hydrosulfuric acid. The reason why excess sulfide reacts with water is because hydrosulfuric acid is a weak acid with small Ka values for both of its ionizable protons. That means that in aqueous solution, the equilibrium favors sulfide accepting 2 protons from water to form unionized hydrogen sulfide. Let's reverse the ionization of hydrosulfuric acid to see what's really happening in aqueous solution. When an equation is reversed, take the inverse of its equilibrium constant. Let's complete the equilibrium by dissolving our metal sulfide in the acidic solution. When equilibrium processes are combined, their equilibrium constants get multiplied together. Although you could calculate the Ksp of the metal sulfide separately from the equilibrium that forms the acid, it wouldn't make any physical sense. Dissolving a metal sulfide in water will always cause formation of hydrogen sulfide. That's why metal sulfides have Kspa values rather than Ksp values. To find the pH where a metal sulfide will precipitate, substitute the concentration of the metal ion and its Kspa value into the Kspa expression. Solve for the concentration of H+ that satisfies the Kspa expression and calculate the pH, which corresponds to the pH where the metal sulfide will be saturated. Above that pH, the metal sulfide is expected to begin precipitating. Let's selectively precipitate copper-2 from iron-2 as sulfides. Just from looking at their widely differing Kspa values, 6 times 10 to the negative 16th and 6 times 10 to the second respectively, they will probably separate. We'd like to separate a solution that contains 0.05 molar of each ion. We'll start with the Kspa expressions for both metal sulfides and substitute in known concentration values. Selective precipitation of sulfides is generally performed on a saturated solution of sulfide ion as aqueous hydrogen sulfide, which has a solubility of about 0.1 molar. We'll solve for the concentration of H+ that satisfies the Kspa expression, meaning that that's the concentration where the metal sulfide is saturated. Calculate the pH from the concentration of H+. At any pH above that value, the metal sulfide will precipitate. Copper-2 sulfide would begin to precipitate at a pH of negative 6.46, which is below a pH value that's physically possible. Therefore, it will precipitate at any pH. Iron-2 sulfide will begin to precipitate at a pH of 2.54. That means to get the best separation of copper sulfide in the precipitate from iron in the solution, raise the pH to 2.54. To find how good the separation will be, find how much copper will be left in solution when the iron is saturated at a pH of 2.54, but has not yet begun to precipitate. Substitute the concentration of H+ at a pH of 2.54 into the Kspa expression for copper and solve for the concentration of copper. Selective precipitation of copper from iron as a sulfide is highly effective since it decreases the concentration of copper by nearly 18 orders of magnitude and leaves the iron behind.